Hello everybody, my name is Vicky Prakash and today I'm going to talk about a presentation by Vasily Volko about better performance at low occupancy. Now it has been thought in the past that to hide the latency you need to run more number of threads per multiprocessor or you need to run more number of threads per block. However, the result of multiplication of two large matrices upon QBLAS 1.1 and QBLAS 2.0 have shown different results. While QBLAS 1.1 ran 512 threads per block and had an occupancy of 67%, and after that it gave the performance of around 128 gigaflops per second. On the other hand, QBLAS 2.0 uses 8 times smaller number of threads per block to around 64, had a lower occupancy of around 33, and despite that it gave a performance which was 1.6 times better or higher than that of QBLAS 1.1. Now in this conversation we are going to talk about how to hide the arithmetic latency using fewer threads, how to hide memory latency using fewer threads, how to run faster by using fewer threads, and there will be a case study upon matrix multiplication using all what we'll be talking during the coming slides. Now before we talk about arithmetic latency, we need to be clear that we should never confuse between latency and throughput. These are two different things. Where latency on the one hand is the time required to perform a certain operation, throughput is the number of operations completed per cycle. It is more of a rate, and the first one is more of a time. For example, an arithmetic operation requires around 20 cycles, whereas a memory operation requires around 400 cycles to complete one operation. This is latency. On the other hand, the throughput of arithmetic operation is 1.3 TFLOPS per second, which comes to around 480 operations per cycle, and that of memory operations is around 177 GB per second, which comes to around 32 operations per cycle. Now the question is how to hide latency. It could be hidden by overlapping it with other operations, which means that while waiting for other operations to finish, we can start doing those operations which are not dependent upon them. Some other which means that while waiting for one operation to finish, we can start other operations before despite waiting for the latency of the first one. But it has its limitations. We cannot start a dependent operation in this time, and this will also help to run the program faster, but it even has this limitation: it can never run faster than the peak. Now let's take an example. There are three arithmetic instructions here: x equals to a plus b, y equals to a plus c, and z equals to x plus d. Now the first two instructions could be run simultaneously, or they are independent of each other when it comes to their execution. However, the third operation, which is z equals to x plus d, this requires the fulfillment of the first one. So this is a dependent one, and it must wait for the completion of the first instruction. Now let's talk about parallelism. John Little says that to get the long time average number of customers in any stationary system, we need to multiply the long-term average rate of arrival of the customers and the time required by them to use the system. When we use this law to find the maximum parallelism, this is nothing but latency times throughput. For example, on a GPU model G80 GT200, where the latency is around 24 cycles and the throughput is of 8 cores per streamlined multiprocessor, the maximum parallelism is 192 operations per SEM. Now there are different ways to hide latency in arithmetic instructions or arithmetic operations. One is by introducing thread level parallelism, and second is by using instruction level parallelism. In thread level parallelism, suppose there are 4 independent operations as in the given case, then we can run these 4 independent operations on different threads simultaneously to achieve a better performance. In instruction level parallelism, we write these 4 independent pieces of arithmetic instructions together and introduce them in pipeline parallelism. In this way, we can achieve a similar result to that of thread level parallelism while introducing all these 4 independent operations or independent arithmetic instructions in the same thread. Now let's see an example. Over here we are performing an arithmetic instruction a equals to a into b plus c for n number of iterations. In the first case, the value of unroll is set to 0, that is, there is no instruction level parallelism. Here, to achieve the peak of 100% utilization or to achieve the peak of 89.6 gigaflops per second, we need at least 576 threads. Now, when we've set the value of unroll to 2, in this case, we are performing 2 operations. We are introducing 2 operations which are independent of each other in the pipeline, and we can get the peak of 89.6 gigaflops per second by using only 320 threads. By the way, all this is dependent upon the result of this particular piece of operation on GTX 480. Now, if we set the value of ILP to 3, that is, if we introduce 3 independent arithmetic instructions in the pipeline, if we introduce 3 independent set of arithmetic instructions in the same thread, we can achieve the desired 100% utilization by using only 256 threads, and for the value of ILP4, we get the same by using 192 threads. So we can say that we can hide the latency either by thread parallelism, which in this case is 576 with the ILP 0, or we can hide that by introducing instruction parallelism, which in this case, if we keep the thread level, when we keep the occupancy to 12.5%, comes at ILP value equals to 4. So we can see that once where it was believed that increasing occupancy is the only way to hide latency, we can also do that by increasing the ILP, and we can say that it is occupancy is, and we can also say that it is not, occupancy is not the metric of utilization, it is just one of the contributing factors. Also, it was believed that to completely hide arithmetic latency, multiprocessors should run at least 192 threads on a device of similar compute capability and 384 threads on the devices of double computing capability. However, it has been found that G80 GT200 uses only 64 threads per SM, and GF192 uses 192 threads per SM to achieve the same results. Now let's talk about hiding the memory latency, where arithmetic latency is around 80, where the latency for arithmetic operations is around 18 cycles and with a throughput of 32 operations per SM per cycle, and the parallelism of 576 operations per streamlined multiprocessor. The latency for memory operations is as high as 800 cycles or even more. The throughput is higher than 177 gigabytes per second, and the needed parallelism is somewhere at more than 100 kilobytes, which means that we need to keep 100 kilobytes in flight if we want to hide memory level latency. This could be done by 3 ways, either by multi-threading, or by using instruction level parallelism, that is more fetches per thread, or by using the bit level parallelism. Now more fetches per thread means that we are doing more work per thread, and so we need lesser number of threads to achieve the same. For example, if we are having if we are fetching 4 bytes per thread, then we need somewhere around 25,000 threads to get 100 kilobytes in flight. And if we are having 100 bytes per thread, if you're fetching 100 bytes per thread, then we need the same work can be done by only 1000 threads. Now let's look at an example. In this example, we are copying a float. In the first example, we are copying only one float per thread. That is A0 equals to source index. Over here, to achieve the peak of around 177.4 gigabytes per second, the occupancy level is 100%. So at occupancy level of 100%, we are reaching somewhere around 84% of the peak. Now let's increase the number of copies per thread to 2. That is, in one thread we are copying 2 float values. That is, A0 equals to source index, and A1 equals to source index plus block dimension dot x. Now we need to understand one thing, that in memory accesses there is no stalling of the threads. It happens only when there is some data dependency, and there is no data dependency over here. Hence we can see that when we are setting instruction level parallelism to 2, we are achieving the peak of around 84% with only 50% occupancy. Now copying 4 values per thread, we achieve the same with around 25%. We achieve the similar peak with around 25% occupancy. Copying 8 float values per thread, we are achieving it to near about 20. We are achieving the similar peak with around 20% occupancy. Copying 8 2 values per thread, we are achieving it to somewhere around 16% occupancy. Copying 8 float 4 values per thread, we are achieving the same at around 8% occupancy. And if we copy 14 float 4 values per thread, we achieve the same at around 4% occupancy. The same peak at that is around 84% peak at 4% occupancy. So there are 2 ways to hide the latency, either by fixing the number of fetches per thread to if we have fetching 4 bytes per thread, then we can achieve around 84% of the peak at around 100% occupancy. Or if we increase the number of instructions per thread, then we can achieve and we are fixing the occupancy to 4%, then we can achieve the same result with somewhere around 200 by fetching 250 bytes per thread. So we see that the previous misnomer that low occupancy always interferes with the ability to hide memory latency, resulting in performance degradation, has completely been disproved over here. Because in the previous case we saw that with 84 we can achieve the peak of around 84% with a mere 4% occupancy. Now let's see how to run faster by using fewer threads. Let's suppose we have certain number of registers per streamlined multiprocessor. Now there are 2 ways to perform the operation. Either we can use more threads by assigning less number of registers